Sir, sir, excuse me, we can't hear you, sir. Sir, excuse me, we can't hear you.
Okay, hello, can you hear me now?
Yes, sir.
Okay, so I think that there was a um, okay, so let me start with this lecture. So we were discussing convex set, and the convex set is like a set in which if we take any 2 points, then the line joining those the 2 points lies in the set itself. So that's the convex set, and that is the line joining the 2 points x1 and x2. Okay, it's written in parametric form, and hello, hello, yes, can you
We can't see any slide. Can't see any slide present. The screen is not sharing.
can you not see the slides?
We can, sir.
Yeah, so you disconnect and join again maybe. Okay, then it should be okay. Yeah, so I continue. So what are these points? Well, we can also write this as, because theta can be taken common, right? So this is like if you take theta common, then this is like x2 plus theta x1 minus x2. Okay, so this is another view of this. So the points on the line are y. Okay, and varying theta, you vary the points on the line. Okay, so another view of this is this. So it's like your base point is x2, and then you are going in the direction of x1 with length theta. Okay, and since the line stops at so x1 to x2, so since the line stops here, so theta is like less than equal to 1. Okay, so you are going in the direction of x1 minus x2, which is the direction x1 minus x2, and starting from the base x2. Okay, and how far you go, it's the theta length you go. Okay, so if you do half, then you will be here. Okay, so this will be this will be x2 plus half of x1 minus x2, which is nothing but x1 plus x2 by 2, which is what we know that the midpoint between two line. So by varying theta, and we can get all the points. And yeah, so if theta is 0, then y is at x2, and if theta is 1, then y is at x. The point is x1. And we also discussed more generally, we can also define so-called convex combinations. So we have seen linear combination, but this is an example of a convex combination. So you can make this plus in general and theta n x n. Okay, so I equals to 1 to n, and here also I equals to 1 to n. So the difference between a linear combination and a convex combination is that in a convex combination, you have these additional restrictions on the scalars, these scalars, right? So these are the restrictions you have, that the scalars are supposed to be positive, and the sum of these scalars in the linear combination must be 1. Okay, and that is called convex combination. So as you can see, convex combination, you can take arbitrary number of points. So I can take this point, and this point. And if I take the convex combination, then it will fill the whole of these things joining this. Okay, so everything in between will be covered, and all this is happening because of these restrictions that you have. Because theta is greater than equal to 0, and sum of theta is 1. If you would have taken just a linear combination, okay, then it would spill over, okay, and then it would cover everything, okay, like we saw in linear algebra. Okay, so but in this case, since you have a restrictions of theta equal to 1 and this is greater than equal to 0, you get within, you only generate points within the boundary joining these points. Okay, so that's the difference between linear combination and convex combination. Okay, by the way, if you have question, you should ask directly by phone. When you are asking question in the chat, chat is not visible to me. When I see the screen, only slide screen is visible to me. So when you are asking question in the chat, I'm not able to see, so I cannot answer your question. Just feel like a class, okay? Just ask question directly.
Sir.
Okay, yeah.
Yes, sir. So here, the linear combination, we can have sets outside, I mean, the points outside of the line that was formed, and in convex, we get the points inside the shape that is formed, right?
Yes, yes, exactly. So the fact that you have these restrictions of the sum of the theta I is 1 and this is greater than equal to 0, that creates a boundary for you. Okay, I mean, a simplest case would be, let us say 2 points, right? So if I take a convex combination, so this will be the convex combination in this case. You can imagine theta 1 x1 plus theta 2 x2. So this is the convex combination involving two points. Okay, so if I allow theta 1 and theta 2 to be anything arbitrary, right? So theta 1 and theta 2 to be anything arbitrary, then they will span all of the all of the points in the space, okay, in 2D, okay, because there is really no restriction on these guys, right? Because if I see them as a vector, then this is my x1 and this is, oops, sorry, so it's very okay, so this is my and this is the vector x2. Okay, so if x1 and x2 are not really in the same direction, then we have seen that, so at the moment they make some angle, then we have seen that they can generate arbitrary many points and fill a whole of the space. Okay, that's what we have seen before. But the moment you put this restriction of theta greater than equal to 0 and less than equal to 1, then so this is my x1 and this is my x2. Now imagine putting these restrictions, okay? So theta is greater than equal to 0 and less than equal to 1, okay? Then you will see that you can only generate points along this line. You can only generate points joining these two. So in other words, you can only generate these vectors, okay, these vectors, or these vectors, or these vectors. You cannot generate anything anything beyond that. Okay, you can play with this. You can write some computer program if you are not sure, then, and plot this these vectors for various values of theta. You can also play a little bit more. For example, let us say you remove this upper bound, okay, of theta less than equal to 1, and just put a lower bound restriction theta greater than equal to 0 and plot these things. Okay, you will get some interesting things. Okay, I won't reveal you, or maybe I may discuss this geometry also later on. But yeah, so you can write a program very quickly, and you will see that the only possibility with these restrictions are the points joining this. But if you have three, then hello. No, yeah, I cannot hear you. Can you speak clearly? Put your microphone close to your mouth. Hello. Yeah, so I gave you example of a line, but then you can play with this. So x1, x2, x3, take 3 vectors. Okay, define 3 vectors, and then moment you put a restriction like this. So in this case, the convex combination is theta 1 x1 plus theta 2 x2 plus theta 3 x3. Now put these restrictions on theta. Okay, so sum of the theta is 1, and then you randomly vary thetas, but make sure that theta 1 plus theta 2 plus theta 3 is 1. You will see that the points it starts generating is only in this, and eventually it will fill all the points, and it will never go outside this. Okay.
Yes, sir. Understood, sir.
Yeah. So now let us move ahead. So this is the question I have. Which of the following are convex set in R2? Okay. So think about this and let me know the answer. So I will wait for a few seconds, and you can let me know the answer.
Sir, A and C.
So what do you think? So these things you can also reply in chat in case you are not able to tell. Okay, so what do you think? There is an option to make a poll. It's called poly or something. I don't know. I will try to figure this out. There is a way to take instant poll. Right now, I don't know. Yeah, so A and C. So Kaustubh is saying only A. Subham is saying A. Kinal is saying A and C. Ayan is saying A and C. Manav is saying A and C. Sarans A and C. So what I see is like either A or A and C. Okay, so most of you are trying to say this A or either you are saying A or you are saying A or C. I think statistically it's like A is a lot more than AC. Okay, I will try to figure out the point.
Sir, is there any reason why the boundary of C isn't filled completely, or it's just an error?
I didn't get what you were trying to say. Can you ask your question again?
The border of the figure C, it is not complete.
Yeah. So that's.
So is there any reason for that, or?
No, I just created some set, right? So, so these are like borders included, and the places where I don't remove, those were like the shaded part is the part of the set. Okay, and if you see the dark boundary, then that is also part of the set. If the boundary is explicitly removed, then those boundary points are not in the set. Okay.
Okay, then only A.
Yeah. So whole shaded part is there, and just to make sure that where is the boundary, we have made a the bold thing, so that this boundary is part of the set when it's bold. In this case, this region is not part of the set. Okay, this region is not part of the set. Okay, these boundary points. Okay. Okay, so now let us try to answer this. So this is convex because I take any 2 points and I join, and the whole of the line is there, any arbitrary point, and this is inside. This is clearly not, I mean, the question itself is giving you a hint that you draw some line and some part of the line is outside. So this is a convex set. This is not a convex set. Okay, and what about this? Okay. Okay, so this is convex set. Okay, so this is like yes, this is like no. This is not a convex set. So C is not a, okay, I should have marked A, B, C. So C is not a convex set because you take 2 points on the boundary. Okay, so let us say you take 1 point here and 1 point here, and if you join, the straight line will be the boundary line, and that part is not in the set. So this is no. Okay, so the answer is like only the first one is convex. Okay, so and then a follow-up question is, what if the square was made into a round figure like this guy? Okay, so what I am trying to say is something like this, and there is a gap, and something like this, there is a gap, something like this, there is a gap. Okay, and something like this, there is a gap. Okay, so imagine that this is a circle. Okay, I could not draw a circle, but imagine that this is a circle and the boundary points are removed like here, here, and here. Now, what do you think? Is this a convex set? I mean, including the shaded region also. Okay, everything inside is indeed part of the set. So what do you think? Will it become convex now? So,
yes, sir.
Yeah. So what do you think in the chat? Yes. Okay, all are yes. Yeah. So now it will become convex, right? Because if the boundary points are taken, okay. So if the boundary points are taken, then if I draw a line, it will be just inside the circle. Okay. So if you're just inside the circle, okay, I cannot draw this because it starts selecting it, but you get the point. If I draw a line joining the boundary points, it is just inside, which is in the shaded region. So then it becomes convex. Okay.
Sir, can you explain once why the square is not convex?
Yeah, square is not convex because this point I took and I took another point, this one, okay, just in the boundary, right? So just in the boundary, I took. Oh, okay. Let me. Strange things are happening. Okay. Yeah. So I don't know why this guy is coming here. Okay. So I took 2 points. And if I join it, then the line joining the 2 points is not part of the square, right? Because that part is removed. But convex set says that the whole line should be inside the set. So in this case, it's not. Okay, because that boundary line itself, that part of the boundary line is missing. Okay, that's why it's not convex. I hope it's clear. Okay.
Yes, sir. Yes, sir.
Okay. So a natural thing is like, can we convexify a set? Indeed, we can convexify. Like you take arbitrary points, and whenever you join, okay, so you take arbitrary points and then you join them, and you include those portion of the line that was not in the set. So you keep doing that. So you keep doing that, and then you can convexify. Okay, so you take arbitrary points and whichever was not there. So if you convexify, then it will become like this. Okay, so it is possible to convexify a set by just taking all the lines and including those lines in the set. Okay, so that's called convexification. Okay, so consider arbitrary points, take arbitrary points in the convex set, make sure that all the points on the line joining x and y is in C, and it is the smallest convex superset. Okay, and if you convexify a set, then it becomes the smallest convex superset. Okay, so any set, so if I, let us say, if I have a set S, if I did a convexification, so convexify, and I get a set T, let us say, then T is the smallest convex set that contains S. Okay, so T is the smallest convex set containing S. Okay, so you don't get anything beyond what is needed. Okay, so you just get enough such that it gets convex, and that's the smallest. Okay, so or another way to say is like, if you already have a convex set, then if you convexify, you don't get anything more. Okay, so convexification of a convex set is the same set. Okay, because you take line joining, but whole line is already there in the set, so you are not getting anything more anyway, right? So convexification of convex set leaves the set is the same set. Okay, now let us look into some geometry. As I said, geometry plays a very important role, and even in data science and so on, we will do some optimization models such as, let us say, SVM and so on. There we will see concepts of hyperplane and so on is essential. Concepts of convex sets are essential because the optimization problem there is a constraint optimization problem. It's convex and so on. The set on which you are trying to solve also matters. So that's why there are two parts. When we are minimizing a function, whether it's a convex or not, that plays a role. And what also plays a role is the domain of the function where we are minimizing the function. So the domain should also be a convex. Okay, and together then we call it a convex optimization problem. Okay, we will come to this later. Okay, you might be thinking, we started with, our goal was to say whether SGD converges or not, and the guarantee for SGD to converge to global minima is when the function has global minima only, right? There are no other local minima. And these are exactly the convex functions, which are like ball shaped. Okay, so they have only one global minima. So SGD is guaranteed to converge because there is no possibility for SGD to get stuck in local minima. Okay, so that's how we started with this. And then instead of studying convex functions, so these are like convex function. I'm not saying set. Okay, so the convex function definition is different. Essentially, they should look like a ball shaped. Okay, they should look like a ball shape. That is convex function. We will come back to that. Right now, what we are discussing is convex set. So there is a fundamental difference between convex set and convex function. Both are related via so-called AP graph and so on. We will see this later on. Okay, it's like very intuitively a function is convex if and only if the area above it is a convex set. Okay, so that's how convex set gets related to convex function. Okay, I will come back to this later on. So instead of studying convex set, we started studying instead of studying convex function, we started studying convex sets. Okay, but both are related because the geometry over which I am trying to minimize matters. Okay. Okay, so let us look into some examples of convex sets. So let us say one is like a hyperplane. Okay, so hyperplane is a like the simplest convex set you can think of, and we know that the equation of a plane is given by this. Like, so equation of a plane is given by A transpose X is equal to B. Okay. So remember from our previous knowledge of high school or senior school, the equation of a plane was given like this. Even during linear algebra review, we saw that these were like planes. Okay, and so it's like in a very high dimensional space, I can talk about a plane, right? So for example. For example, in R2, right? In R2, the plane is like a line. Right? So the concept of a plane is like here we are talking about. It's not necessarily only R2 plane. Okay, so that's why. Like in R3, the planes are like the usual plane that you might be thinking, right? But in R4, the planes look like plane dimensions are like R3. You see the point? So in R100, okay, so the planes will be like R99 dimensional, right? Okay, so planes are not always like R2. That's what I'm trying to say. So if in R2, the planes, I will say it's, I mean, we gave it a line, but in general, we can classify everything like this, right? That we can just use plane term more generally. That's what I'm trying to say. Okay, so so that's why we have a very general definition here. We are not saying how many A's are there. So if I write A1 x1 plus A2 x2 is B. Okay. Okay. So then we get a plane in R2. Okay. So then A1 x1 plus A2 x2 plus A3 x3 equal to B. Then I get a plane in R3. And so on. Okay, so this plane in R2 will be a line here. Plane in R3 will be depending on like two variables and so on. So that's the general equation of a hyperplane. Okay, so now the question is hyperplane convex? Okay, so if you imagine, then it looks like a convex only because it's a plane, right? So so I take any two line on the plane, I end up in the plane. But we can concretely prove this, right? So let us take two arbitrary points, x1, x2, be in the hyperplane. So let us denote this by h. Okay, and let us say that theta is greater than equal 0 and less than equal to 1. We are using the first definition of convexity. We take any arbitrary points. So let us take take this arbitrary points. And what we have to prove is that theta x1 plus 1 minus theta x2 is also in h. Okay, that's what we have to say. We have to prove for these values of theta. So since x1 and x2, is in the hyperplane, then what we have? Then we have A transpose x1 is B, and similarly, since x2 is in H, I have A transpose x2 is equal to B. Okay, so these two relations I get because x1 and x2 are in H. And now I have to verify whether this is in H. So to verify that this is in H, what I have to do check is A transpose of this this new point. Let us say this is like Y. So this is A transpose and theta x1 plus 1 minus theta x2. There is a parenthesis should be here, not here. Okay. Okay, so we have to check whether this comes out to be B. If this is equal to B, then Y will be in the H. Okay, let us see. So this is theta I take common. So A transpose x1 plus 1 minus theta I take common. And then A transpose, because 1 minus theta is scalar, right?
Hello, sir. Hello, sir.
Yeah.
Sir, A and B should not be same, right? They can be different. Like
No,
A1,
no.
A1 was
No.
B1.
No, A and B are fixed. A and B are fixed here. Okay, in a plane A and B are fixed. If I change, then I will get different planes. Okay, so in a space I may have different planes depending on what are the A and B's. So I'm considering some hyperplane. So if I consider some fixed hyperplane, then A and B are given to me. The only thing that is changing now is the x here is a variable, and so basically it's saying all the points in this, or all the points that satisfy these equations or these equations, A and B are fixed. Okay, so here I have A transpose x1 is B, so it is theta B plus 1 minus theta A transpose x2 is B. So this turns out to be B only. Okay, so since it satisfies A transpose Y is B, so this implies Y is in the hyperplane. Okay, so that proves that that I took any arbitrary point, and the line joining the two arbitrary points here is also in the set H. So this means that this is a convex set. Okay. So examples of, as I said, example of hyperplane in R2 is a line. And these things can be used in, as you can see, it's like some data points is there in the green, and then some data points are there in the red. And a classification problem is like finding a hyperplane that can separate these two classes. So if your model learns this hyperplane, so model learns this hyperplane. Okay, so that means that that you have trained your model, and then after that, if a new data point comes, let us say comes here, then you will check whether this point is on this side of the hyperplane or on this side. If it is on this side, then you will say that this is one of the green points. Okay, so this is like classification thing works. The natural question is, what are the guarantees that you will find such hyperplane? Right, what is the guarantee that you will find such hyperplane that can separate these two classes? Right, so there is something called separating hyperplane theorem, and these things are assumed when you are doing data science problems. You assume that if you are building a linear classifier like here, you assume that because if your data is not like if you're thinking about linear separability and but your data's distributions are such that they are like in some sense like to say that like if I convexify these points, right? So if I convexify, then if I convexify them, then I will get a convex set, obviously. And if I convexify them, then I get a convex set. And after convexification, they should not like intersect. Yeah, that's the intuition that's it's saying. So hyperplane theorem builds on this. Okay, so it's an existence proof. So we will try to prove this later on. Okay, so I just gave you a little bit of hint of what we are supposed to do. Okay, But if it so happens that like red points and green points are intermixed, okay, then if I convexify, then this guy will everything and this guy will mean everything. So after convexification, their intersection is not empty, okay, and hence such data are not linearly separable. Okay, you cannot hope to build a linear classifier on that. Okay, you see the point, like how. So yeah, intuitively I told you, but one can concretely prove these things. Okay, so in fact we will prove this thing. Okay, so for the moment we are just talking about sets and convex sets. So let us come back to convex set and so on. So is hyperplane convex? I just proved to you now. Okay, so it's fine. And one of the things that you should recall again is how do you see this these geometrically, right? So you can take some point on the plane. Let us say there are like 2 points on the plane, x node, okay, and then let us say some point x on the plane. Then A is nothing but a line. It's like a normal to the plane. Okay, so this is the normal form of the plane, if you recall. Okay, so normal form of the plane. Normal vector dotted with the vector in the plane. Okay, is A, if you recall, something like this, right? I mean, it will be 0 if you really want to be strict here, and the intercept will be found by finding where it's at point 0 where it is. Okay, so at x equals to 0, if I put here, then I know where it is at the point. Okay, so equation of plane is derived by the fact that let x be a vector on the plane and n be a normal to the plane. Okay, so definitely the dot product should be 0, right? Now the vector, whether it is passing through the origin or not, that will decide whether you will get a b to be 0 or not, right? So either the vector doesn't pass through origin or the vector passes through origin. If it passes through origin, then x dot a will become a b here, and then you will have A transpose x here. Okay, and if it doesn't pass through origin, then yeah, so then your b will become 0. Okay, so you can recall these things from yeah. So in general, if b is not equal to 0, then it's a plane not passing through origin, because x equals to 0 does not satisfy the equation. So plane doesn't pass through origin. If b is non-zero, then plane doesn't pass through origin. Okay, so now there is another geometric object which is called half space. Okay, so if you compare this, the equation was A transpose x equals to b. Now this is A transpose x greater than equal to b. Okay, so what will it do? Right, so if you have equations like this, what does it mean geometrically, right? A transpose x is greater than equal to b. Right, so to understand this, what you can do is, like, first you draw A transpose x equals to b, okay, and then the concept of whether it is greater or less will be whether it is on the upper side or whether it is on the lower side. Okay, so that will determine whether it's on this half space or this half space. Okay. A half space will partition your space always into 2 parts. Okay, because I'm always talking about a hyperplane here. Okay, so this is like some hyperplane. Ax equals to b is a hyperplane in the ambient space. Ambient space is the space where you are working in. Let us say the space we are working in is Rn. Then the hyperplane will be Rn minus 1, Rn minus 1 dimensional. Okay. Look, hyperplane as such are not a vector space unless it passes through the origin. Okay, so do you see this? So hyperplane are not vector space. So hyperplanes are not vector spaces in general. Okay, I'm talking in general, but there are cases where it will become. So if I go back and see this set, okay, so is this set a vector space? Well, if this is a vector space, if this is a vector space, then we know from the linear algebra review that for a space to be a vector space, origin should be there. Okay, the 0 should be there, 0 vector should be there. Then a 0 vector should be there. Okay, so should be in H. But that 0 vector will be in H only if B is 0, right? So this happens only if B is equal to 0. In other words, what we are trying to claim here is that hyperplane is a vector space if it passes through the origin. Okay. So in general, hyperplanes are not a vector space. Okay, unless it passes through the origin. Okay. Okay, so now let us focus on the half space. Okay, so is half space also convex? So let us consider so hyperplane will give you two half spaces, regardless of which dimension you are working in. There will be only two sides. As I said, if you are in R2, okay, then a hyperplane will decide a half space. So let us say this is my hyperplane in R2. Then this side is one half space and this side is another half space. So it partitioned R2 into two parts. Okay. Similarly, you can extend this to R3. If you extend this to R3, or I can show you a figure from here. So this is R3 and this is a hyperplane in R3, and this is like extending beyond everything. Okay, so it's not like I have restricted this, because hyperplane are not restricted. Okay, so you will see that the upper part is one half space and the below part of this plane is another half space. So in R3 again, a hyperplane divided my space into two parts. So a hyperplane always divides my space into two parts. Now this thing can be generalized even to Rn. Then hyperplane is n-1 dimensional. Look, I'm saying n-1 dimensional, but dimension only makes sense for a vector space we have seen. Okay, but there is a concept of something called affine dimension. Okay, so we can talk about dimension in the sense of affine dimension. Okay, otherwise we talk about dimension only for vector space. But even though this hyperplane may not pass through origin, I can consider something called affine dimension. So affine dimension is n-1 dimension, and so this will again split the original space in two half. Okay, and it's because either it's greater than equal to B or it is less than equal to B. So there are like only two options. Okay, so then you will have the first half and then the second half. So half spaces you have are only two. Okay, and now the next question is whether this is a convex set. Okay, so to prove that this is a convex set, what are we supposed to do? Okay, so let us say we want to prove this as a convex set or not. Okay, so let me clear this. Okay, so let x1, x2 be in this half space. Let us say I call it H again. Then this means that A transpose x1 is greater than equal to B. A transpose x2 is greater than equal to B. Now I am looking for points like this: theta x1 plus 1 minus theta x2, and then I have to do A transpose of this. Okay, and this is theta A transpose x plus 1 minus theta A transpose x2. A transpose x is greater than equal to B. So this is greater than equal to theta B plus 1 minus theta, and this is greater than equal to B. So again I put B here. So theta B gets cancelled. So this is B. So overall, this is greater than equal to B, right? Because this is here. Okay. So indeed, indeed, a half space is also a convex set. Okay, it was evident from here because if I imagine this space, I take any 2 points, the line joining is there. So intuitively, it was clear. Okay, so this is a geometrical view of the half space. Okay, so I have this figure here. So the points that are on this side of the hyperspace, by this side I mean the points that are closer in angle to A, or in other words, making acute angle. Okay, so those will be in this side. Okay, so for example, this point is making acute angle, this point is making acute angle, this point is making acute angle, this point is making acute angle. Okay, so if someone gives you a point, how do you know it's greater than? So you take that point. Okay, and so geometrically it means like which are the points that are making an acute angle, because if not, then this will reverse the sign. Okay, because this is an inner product, right? So this is an inner product here, right? A transpose X is an inner product of A and X. So the way it is characterizing the points is like the points X which make an obtuse angle with A, those will be this side, and the points that make acute angle with A will be this side. So that is how you can characterize also based on the angle. Okay, because A transpose X will be norm of A, norm of X. I hope you did the linear algebra review, and then cosine of the angle between A and X. Okay, so cosine of the angle between A and X, right? Remember that signs are not changed by these guys because these are norm. So norms are, norm of a vector is always positive. Okay, that's the definition of the norm. If you have not gone through linear algebra, then review that. Okay, so the sign is.
So this is only X naught is an origin, right?
Which one?
The acute.
Yeah.
Yeah, only B0 is applied, right?
Only B0 is? I didn't get your question.
You told that if it is an acute angle, then it's on one side.
Yeah,
That's possible only if B is 0.
Yeah. So it's B0, but yeah, we have to take it into account. Yeah, you are right. What we have to do to actually make it based on the acute angle and so on is the following. Yeah, you're right. So we have to make a little bit of adjustment here because so let us say, so at what point we achieve B, right? So let us say that point is X naught. And at that point, it becomes B. So we have to substitute B here. And then so A transpose X is greater than equal to, so B is A transpose X naught. So this implies A transpose X minus X naught. Okay. And that is greater than equal to 0 or not. Okay. So we have to first find a point where it achieves B. Okay, so let that point be X X naught. Okay, and then any point that you take, and then relative to this X naught, right? So if I take a point here, so then this is like, let us say point is P. So then the way I will compute is P minus X naught angle with A. Okay, but if I take some point here, which is X minus X naught, but then this makes like obtuse angle, right? So we have to do a little bit of adjustment, like I said here, because it's a general case where we have B here. So imagine that x naught is the point where we have A transpose x naught is exactly equal to B. Okay, and then I can take any point here. Okay, actually x naught could be any of these points, right? But it doesn't matter because the normal is always like this, and any vector point in your plane is characterized by this. So this point and then angle that is making with A minus yeah. So angle it is making with the A. Okay. So what angle A is making with x minus x naught, or let us say all the points on this side are y, all the points on this side are x. Okay. So for all these points which are on this side, it's like less than equal to B, and for all the points which are on the right hand side, y minus y naught is greater than equal to B. Okay, like you are allowing those x and y to be also on exactly on this. So in those cases you have equality here. Okay. So these geometrical meaning are important because that's when yeah. So is the half space convex? So we have proved this. What is the yeah, yes.
So another question. So I consider this half space. So could you show mathematically how the affine in the affine dimension? So suppose x is in Rn. So how the affine direction will be now dividing in half, and like we have the arbitrary option to make the affine angle in some space, or it will be fixed?
No, I mean, the fact that it's dividing it in half comes from this only, because I have only two relationships, either greater than equal to 0 or less than equal to 0. I mean greater than equal to B or less than equal. So there are
no in the affine. Okay, we are saying that A transpose X is in itself in an affine direction, in an affine space. Okay, got it.
Yeah.
Thank you.
The fact that you going to get only two half space is either you are making acute angles with A, or you are making obtuse angles with A with the normal. A normal could be in any big dimension, it doesn't matter. So you always get only two half space. Okay. Okay, but you should remember that if your ambient space is n, then your the plane you should consider is n minus 1. Only then you get like two half space thing. Okay, so okay, so yeah, so okay, actually I did this here only. Okay, so what I said before actually is done here. So I could write this as x minus x naught, like I described in the previous case, and then if it makes an acute angle, so x1 is not in the half space because it makes an acute angle, because like x1 minus x naught, this okay is like greater than 0, and x2 is not in half space. Is x2 in half space? No, yeah, so x2 is in the half space. We are talking about this. So is x2 is in half space? Then yes, then because I think the question should be x2 is in half space. Yeah, so because in this case it makes obtuse angle and it satisfies this criteria, so hence it's in the half space. Okay, so this is something characterized by now. Now let us consider some other convex set. I mean set, but whether they are convex or not, I don't know. Okay, so let us consider this set. Set of all x in Rn such that L norm is 1. Okay, so in case someone did not define this for you in the linear algebra, then the way I can define this L norm is the following. So these are like components of x1 to the power L plus x2 to the power L plus x, let us say it's n dimensional, right? So xn to the power L, and then you take 1 by L lth root. Okay, so the familiar norm that you know is the 2 norm, where L is 2. So in that case you have x1 square plus x2 square plus dot 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 plus xn square. you take square root. Okay, so this is the usual norm, Euclidean norm that you are familiar with. Now I have generalized this norm by taking L, and L could be let us say rational number, but any positive rational number. Okay, so it is easy to prove that this satisfies the norm property. Okay, so in linear algebra review, I think they might have told you what is a norm. Okay, so norms have certain conditions, right? So norm of a vector is always greater than or equal to 0. Norm is 0 if and only if the vector itself is 0. Then there is something called triangle inequality. So this is less than or equal to norm x plus norm y. And when I'm talking about norm, so this thing, all these things are satisfied for L rational number here and positive number. With this definition of the L norm, you can prove. Sometimes it may not be that trivial to prove, but it can be established that this will be a norm. I have shown a picture of the norms here. Okay. So if you take L equal to 2, then this is the usual usual circle. Okay. So if two norm of x is equal to 1, then this is nothing but circle with radius 1. Okay. And if one norm of x is 1, then you get this diamond shape. Okay. You can verify these shapes by doing a plot of these. Like, so one norm of what does one norm mean? So this is like x1 to the power 1 plus x2 to the power 2 plus dot 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 plus xn, and that turns out to be 1. Okay. So so this is this will look like a diamond shape. Okay, like this. And then you can take half. Then this norm will look like this. Okay, so this way you can keep doing this. So the variety of this. So now here the question is whether S is a convex set. So what do you think? Is S a convex set? So let me know in the chat for any, like for which L. Okay, so do you think it's a convex set? And if yes, for which L it's a convex set?
Sir, for L greater than or equal to 1, it's a convex.
L greater than? L greater than or equal to 1. But so like everyone is saying yes. So Manish is saying no. Ashok is saying no. Manav is saying yes. Sweta is saying yes. Tushar is saying yes. Someone is saying if it is greater than or equal to 1. But do you see this set concretely? Like, do you see this? Because there is equality here, right? Now what is your answer? Can you recheck and tell? Yeah. So Ayan, it's circumference with no area. So it's a no. Santanu, it's a no. Okay, now you corrected yourself. So actually it's only the boundary points are there, right? Because it's a equality, right? I did not say it's less than or equal to 1. Okay, if I say less than or equal to 1, then the area inside would have been covered. But just like the hyperplane thing, right? If I say equal to 1, it's just that whole line only, right? So in this case, it's like only these boundary points. So if I don't do, if I put equality, then none of them are actually convex, because if I start from infinity, so infinity will become the square, okay? Well, any 2 point inside is not contained in the set because only boundary are there. So none of them will be convex, just very trivial. Okay,
Sir,
it will
for L is equal to 1, it will be convex, right? Because the boundary points are only the points inside the set. Yeah, okay, sorry. Understood, sir. Understood.
It is always only boundary, right?
Yes, sir. Understood, sir. Sorry.
Okay. Yeah. So none of them are convex actually. But it is interesting to see what if I change the equality to less than or equal to. Okay. So in this case, answer is none of them. Okay. Now I change this to this. Okay. Okay, x0 is just a offset, you can forget x naught. You can put 0 there, and so that the center will be origin, right? But you could have made this norms around some x naught. Okay, so it doesn't matter. But what do you think now? Okay,
For L equals to 0, it would be there, right?
L equal to 0. I did not say, right? I said positive L. Okay,
Okay.
L strictly greater than 0. Okay.
Yes, sir.
Yeah. So in this case, what do you think? Is this? I have not done explicit setting of the area here. Okay, because of the I just took a figure, but consider this now, less than equal to. Now area inside will be included, including the boundary, because equality is also there. Now for which L it's a convex? Now tell me your answer in the chat. So what do you think? So Rohit, is L greater than equal to 1? L greater than or equal to 1, it's a convex. That's what Rohit is saying. So what do you think? Someone is saying all L. Are you sure all L? Okay, so here like I'm missing this L here. Okay. So are you sure like all L? Because some of the examples are already contradicting your for all L, right? In R. Okay. So yeah, so there are 5 likes for L greater than equal to 1, and this is the correct answer, because L greater than equal to 1 only. So this is the L equals to 1 case. This is the L equal to 2 case. That's when it's not going inside, right? Any set that has inward what is called? There is a word in English, right? It's called inflation or something, right? Inflated or deflated. Yeah. So it's like a balloon, right? If it is fully inflated, I guess, then it will be a convex set. It's something like this. But if something is like this, it bending inward, then it's not. So these guys, for L equals to half, let us say, starts bending, right? And similarly, for L equal to 1 by, let us say 3 by 2, not 3 by 2, but yeah, it's just above this, right? So yeah. So just below this and above this. So let us say 1 plus 1 by 2, right? So this will be this, and then some L will be this, some L this. So there will always be some inward bend inside, and that will not make it convex. So below L equals to 1, less than equal to 1, it's always like not convex. Okay, because in this guy, like I took this point and this point. If I join, then some part here is going outside, just outside. Okay, so then yeah, so that's the answer. Now let us continue. So L equal to 1, 2, 3, dot, dot, dot. Okay, so it should be dot, 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 because it can go up to infinity. L equal to infinity is also a valid norm. Okay, and okay, you can wonder what is L infinity norm, right? So L infinity norm is defined to be like this. It's a max of mod of x1, x2, xn mod absolute value. Okay, so you take the maximum of the absolute value of the component, and that is defined as the infinity norm. And if you plot this, you will get this square-like thing. Okay. Okay. So let us move to some other. We have half an hour left. So let us look into some other sets. This is so-called ellipsoid. So as the shape suggests, you can see it's an ellipse. Ellipse is just the boundary. And if you take the points inside by doing this, then you get the points inside and it becomes ellipsoid. And this is centered at xc. So that's why it's slightly written in a different form to take into account the center is xc and not 0. Okay, And P should be symmetric and positive. P is a matrix here. Okay, so P is a matrix. You may not have seen equation of an ellipse in this form, right? But this is an ellipse actually. Okay. I can take some arbitrary example. Let us say. Okay, so P is like let us say matrix like this 1 0 0 2. Now let us say the center is origin, so x is 0. So then what is this set? Set of all x such that x transpose px is, let us say I'm talking about ellipse and not ellipsoid. So let us say I'm talking about this. So do you see that this is an equation of an ellipse? It is because x we can write this as x1, x2. So this is the transposed of that, and this is like 1 0 0 2, and this is x1 x2. Okay, so if we work out this, what do we get? Right, so this is like x1 square plus 2 x2 square is equal to 1. Right, so this is an ellipse, right? Because the standard form, if you recall, of the ellipse is like 1 square, okay, or like square root 2 square, right? And then x2 square by 1 square is 1. Okay, so this is of the form x square by a square plus y square by b square is, okay, let us say 1. Okay. So this is the equation of an ellipse, but it can be compactly written using matrices. And if it is not centered around 1, then centered around 0, then we have we can make use of these xc, and we can subtract it and so on. Okay, so okay, so if we look into this now, this is the set. Okay, so P is 70%. So is this a convex set? Okay, so the question is this a convex set? Well, from picture, it's a pretty much a convex set because it's an ellipsoid. So ellipse is like inflated, and then all the points inside. So obviously it's a convex set. Okay, because line joining will be inside. But you can prove this also explicitly. Okay, it's again should be like a straightforward thing, like x1 x2 is in ellipsoid. Then this means that x1 minus xc transpose p x1 minus xc is less than equal to 1. Similarly, x2 minus xc transpose p x2 minus xc is less than equal to 1. And then you have to check whether theta x1 plus 1 minus theta x2. Okay, so whether this is in the set. So if this is there, then we have to do this. It becomes long now, but it should be possible. Okay, or this is like theta x1 plus 1 minus theta x2 minus xc. Okay, so if you can prove that this is less than equal to 1, then you will show that this point is indeed in the ellipsoid. Okay, so this should be like a little bit long calculation, but it should be possible to like show this, right? So it's just that the terms will be different. Okay, maybe I will leave this as an exercise. It's just taking time, but I'm sure you can do this. Okay, so you know what to do. Your goal should be to prove that, because geometrically I know that this is convex, so this must be less than equal to 1. Okay, so it must be possible to do this. And what you will use is these two things. Okay, so try to do this. I will put this as an assignment also, so that you surely do this. Okay, and solution to the assignment or any doubt will be in the tutorial. Okay, so this will be a convex set, and this is the ellipsoid centered at xc. So the length of the semi-axis of the ellipsoid will be given by square root of lambda I, where lambda I are the eigenvalues of P. Okay, this is like a mouthful. Like there are so many things. Why is this case? Why is this the case, right? Like the semi-axis are somehow related to the eigenvalues of P. Okay, why is this? So there are like two axes we recall, right? So one is called so-called major axis, and in ellipsoid another one is called minor axis. Major and minor axis. So what this is trying to say is the major axis length will be given by square root of lambda I. Okay, and the minor axis length, okay, major axis, but it did not tell me which one. Like there are two eigenvalues because P is a 2 by 2. Let us focus on the 2 by 2 matrix. Okay, or the ambient space that we are talking about, the space that we are in reference is R2 here, and in this we are talking about the ellipsoid. And P, since X are 2 dimensional, P has to be 2 by 2 matrix. It's applying from the both sides. So what it is trying to say is like major axis is like square root of some lambda I. So it could be one of the lambda i's, and other axis is the other lambda. There are two lambda, right? So now, like, how do we digest this fact? Right. So how do we digest this fact? We can do like what we did but we can take, let us say I show you an initial intuition based on some matrix. Let us say some arbitrary matrix I take, not arbitrary, but let us say some special matrix I take. Okay, so let us say I take this diagonal matrix, and in this case eigenvalues of P are now easy because it's a diagonal matrix, so eigenvalues are on the diagonal. Okay, so eigenvalues set is just A and B. Okay, even for this, let us verify this claim, right? So if and let us say the center is at origin, because center doesn't change. I mean, it has not much to do with axis length, right? So then what we are talking about is X transpose PX, right? So this is transpose, so PX. So this is how much? So if you do this, then this is like again like before x1. Okay, let me do it here. So x1, x2, and P is like A0, 0, B, and x1, x2, and this is so this is equal to 1. So this is like what? This is like A x1 square plus B x2 square is equal to 1, right? And I divide by AB. I divide by AB both sides, right? So this is like x1 square by B plus x2 square by A is equal to 1. And we know that one of these are major axis and minor axis, right? So a square root of B is the major axis, right? So if we write this in the standard form, then this is square root of B squared plus x2 square by square root of A squared is 1. Now we can read out the axis length. Now let us say without loss of generality, let us say A was the larger eigenvalue and B was the smaller. If A and B turn out to be equal, then it becomes a circle, not ellipsoid, right? For it to be ellipsoid, it must be that the eigenvalues are different. Okay, so so let us, without loss of generality, let us say that A is greater than B. Then the major axis is square root of A. So let us say square root of A, and this is like square root of B. And if we recall, square root of A is nothing but square root of the eigenvalue. So A was actually the eigenvalue of the matrix, and square root of B was also the eigenvalue of the matrix. Okay. So that's what it's saying. It's the square root of the eigenvalue. So how much you will stretch along the major axis will be determined by the square root of the lambda max. Okay, and how much you will stretch in this direction will tell you it will be square root of lambda min. Okay, square root of lambda min. Remember that we are talking about R2 here. So R2 is a two-dimensional, right? But ellipsoid can be multi-dimensional. Okay, so I don't know how to draw this, but so let us say like this is 3D, right? So you will have three axes, right? You will have three axes, and how much you stretch in one of these direction will depend on like on the lambda I. Okay, lambda 1, lambda 2, lambda 3, and so on. Now, what is missing is the general case where P was any matrix, right? So let us say A, B, C, D. So the question that is remaining is, does it still hold like the major and minor axis will still be along the lambda I, because the result that I'm trying to say, I did not assume P to be a diagonal matrix. So this I will post this again in like the assignment. Like why for a general matrix, why it will be the lambda, the axis will be along lambda I. So you may take this general matrix, you may form this general product, and you may want to bring them in standard form. When you are bringing them in standard form, like this standard form, I mean, because there should be a square. These terms that you are getting in the denominator, they should somehow involve lambda I. Okay, so these calculations you may try to do. Okay, how like 2 by 2 matrix, like you can do. Okay, so this is something you can do it. Okay, as an assignment. Okay, so I have another like 10 minutes. So as I said, if it so happens that P is like a diagonal, like A is equal to B, like I said before, if A is equal to B, then I can substitute this as A. So this I can write this as A 0 0 sorry 1 0 0 1. So this is like A times identity, right? I could square it also, it doesn't matter without loss of thing. So yeah, I mean, what will happen if it is, yeah, so what will happen if it is A is negative, right? So that would be interesting to see. Like you can, like can A, so what if P is like this, A 0 0 A, but A is negative? Does it like still turn out to be a ellipsoid?
It won't be positive, definitively.
Yeah, because yeah, so it won't be possible to make it 1. Let us say the right hand side is 1, because left hand side will be like negative, right? I hope all of you see this, right? So A negative is like we rule it out. Okay. So since these guys are supposed to be positive, we can always replace this by some square. Let us say R square. So in case 1 1 and 2 2 entry are 0, sorry, equal, and so on. So what it is trying to say is this, right? So P is R square identity, and that it becomes a ball. Okay, so we call it ball. Okay, so if both this and this entry is 0, it's a diagonal first of all, and then these are same and positive, then it becomes a ball. Or in the case of R2, it's a circle. Okay, because there is equal stretching in all direction. If you have equal stretching in all direction, then it's a ball. We call it ball because we are talking about any general space. Okay, not just R2. So R2 it will be a disk, but in general, it's in any arbitrary high dimensional space, it's called a ball. Another representation of an ellipsoid is the following. This won't be very intuitive to you right now. Okay, and okay, I forgot to tell you other thing, like P is symmetric and positive definite. Okay, that's also an important criteria here. And positive definite, what does positive definite mean? Say matrix P is symmetric and positive definite if first of all it is symmetric, and then X transpose Px is greater than equal to 0 for all X not equal to 0. Okay, that's the definition of symmetric positive definite. So only then you get an ellipsoid. Okay, if you take a non-positive definite, for instance, if you take, and what are the eigenvalues of a positive definite matrix? All are positive. Okay, that's we saw in the linear algebra. So, but let me say if I don't make it all positive, let's say eigenvalue 1 is negative, other is positive. So overall it is not SPD. If it is not SPD, then it won't be an ellipsoid. Can you tell me in this case what it will be? What is that geometrical object? Can you tell me in the chat?
Hyperbola.
Hyperbola, yes. So if it has one negative and one positive, then it will be like a hyperbola, right? It's like ax square minus b x square minus y square divided, and then individually they have denominators a and b and so on. So that will be equation of a hyperbola. Okay. So that's the difference. If P is not symmetric positive definite, it's an hyperboloid. Okay, so I can already define hyperboloid. Hyperbolic manifolds are becoming very important in let us say NLP domain. There are reasons for that. If I have time, I will discuss that. There is some optimization link there. Okay, it's due to the embedding. Okay, because similar things should be similar and so on. In the uniform spaces like balls, it's not a good thing. Okay, and also how to do embedding in a very compact way. There are some ideas behind why one should choose hyperbolic embedding. But once someone starts embedding into such space, then you have to talk about minimization on that, not on the Euclidean, but because someone had some, let us say, some word data is there, and then it's now put into some hyperboloid. Okay, so some hyperboloid. So now data mapping you did because it's efficient. Let us say, okay, if you do it like this, because the relationship between the words and whatever is preserved in a nice way in hyperboloid. But now the problem is now data is sitting here. Okay, and you are learning a neural network. You are building a model based on the data that is sitting on the hyperboloid. Now it becomes a bit tricky. Now you have to do minimization, maximization on the data now embedded in this. So there are papers on neural networks on hyperbolic manifold. Okay, so there you have to do optimization on manifold. Okay, so that's not covered in this course. Okay, so so what I was trying to say is okay, we have so what I was trying to say is like the another representation of an ellipsoid is like this: xc plus a times u. It's like you start from a center and you take a vector that is less than equal to 1. Okay, so that's very important. Now let us recall what we did in the convex in the case of a line, right? So if I had a line, I started from x2 and then I went in the direction of x1 minus x2 and with a length of theta, and then I added like this, right? And then this gave me the points on the line joining x1 and x2. This in some sense is a generalization of that. Now the source of your of your point generation, like base, is like xc, and then from here onwards you are going in the direction of u, but this u is like should be like less than equal to 1. Okay, so this is like less than equal to 1, and then you multiply by a. Okay, so it's like I am at xc and then I'm multiplying a matrix A, and obviously the way the matrix A is, it will create a stretching based on the way eigenvalues are distributed. So let us go back to this form, let us say, okay, A or yeah, we changed the notation. We were talking about P, but okay, never mind. What it will do, right? What it will do? We have seen from the eigenvalue and eigenvectors in the linear algebra review is the vectors that are, let us say, along this direction. So I know that this is the largest eigenvector direction. Let us say this is the u, and this is the v. This is the smallest eigenvector direction. So the moment the vector is somewhere along this, let us say the unit vectors were this. Okay, so let me draw also the unit vectors. So this is the ball, norm u is less than equal to 1. Yeah, so I hope I don't contradict anything else. I was thinking like, should it touch even the minimum 1, but there is no guarantee actually. It should necessarily touch minimum 1 because even the smallest eigenvalue can be like, yeah, like it can scale a lot more than the unit. Okay, so anyway, so let us say this was your norm u less than equal to 1. This is what we saw in the previous case, that this is norm u less than equal to 1 ball. Okay, and everything inside it. Now we want to apply the matrix A on all the points here, right? If it so happens that u is along the eigenvector direction, okay? So I used u here, so that can create an issue here. So let me use w here, okay? Because u is already used for the unit vectors. Now let us say w is a vector along the largest eigenvector. I mean, let us say u is any vector that is along the largest eigenvector, which is w. So that means that u is some alpha times w. Okay, that's what it means, because saying that u is along w, then this is what it means. So what is the action of this? This on u, right? But what is also known to us is that norm of u, because the way I should choose is like it should be less than equal to 1. So let us say alpha was chosen in such a way that this is indeed satisfied. So what will it do to u, right? So if I multiply that, then but this is like alpha w, right? So which is an eigenvector of this. So since this is an eigenvector of this, so I take alpha common. Okay, so since this is an eigenvector, this will be some lambda times w itself, right? Okay, so it's like lambda times w itself. So overall, what I will have is alpha lambda w. Okay, but so this is the eigenvalue, right? Now, since this is the largest eigenvalue, because I'm talking about this, it will stretch. Okay, although u that you started with where like let us say just focus on this point u on the boundary, right, where the norm is exactly equal to 1. But since lambda is the largest, let us say lambda is like 500, right? So it is going to stretch this more in this direction, because lambda is the maximum eigenvalue, and let us say it is 100. So unit vector was here. Okay, unit vector was here, and it will be scaled by 100 in this direction. And similarly, what happens in this direction depends on the other eigenvalue. Okay. So if it is like less than 1, then it will contract, and the point will be somewhere here inside this normal ball. Okay, it will contract. So this way, even points which are like these points are neither along any of the eigenvector direction. But in those cases, what it will try to do is, okay, I'm already out of time. I will continue with this because there is a little bit of deafness here. Okay, so I will try to explain this in the next class. I'm quickly going to like stop recording, otherwise it splits into 2 parts. Okay.
Sir, could you please share the PDF?
Share the video. Yeah, I shared this video and they